to be here. It's great. I was here as a first-year graduate student like 15 years ago. It's good to be back. So I'm talking about colored not Floer homology. I'm going to start with an introduction. Not Floer homology, as we know, was defined by Ojrat and Zava. And its kind of simplest version is h of hat, h of k hat. Well, okay. Say Ojrat, Zava, and Rasmussen. Simplest version is h of k hat of k, which is a bigraded F2 vector space. This bigraded, it has two gradings. One grading is called massive grading. The other one is called Alexander grading. And it categorifies Alexander polynomial, which, well, the good thing about speaking on the last day is that we all have heard lots of things about these things. I just want to show you in a slide that Alexander polynomial is defined by this oriented skin relations. So it categorifies Alexander polynomial, meaning that we can compute the Alexander polynomial of a knot by taking the graded order characteristic of not Floer homology. Well, we are not going to do that, but -1 to the I dimension, say, rank of h of k hat. Let me just keep the same notation as what I have here. Just use M for massive grading. S, K, M, T to the S. Right? S, I'm going to use S for Alexander grading and M for massive grading, and those are the two gradings we have. Okay. If you change in the D category for level, if you change the coefficients in our skin relation, we'll get the Jones polynomial, right? And Jones polynomial also has been categorized around the same time as Alexander polynomial. The categorification, we have heard a lot about it. It's called Kovanov homology. Well, one which was defined by Kovanov. It's also not K, it's also a bigraded F2 vector space. And these two theories are nicely related. One of the relations is, well, we have heard to talk about it earlier this week, which there exists a spectral sequence from Kovanov homology to not Floer homology, to be more precise, reduced Kovanov homology of the mirror image of a knot K to a not Floer homology of K. It was conjectured by Rasmussen, and it was proved by Nam recently. Right? It was proved over Q by Dallin and over F2, Zima 2 coefficients by Nam. That we heard to talk about it earlier this week. Okay. On this side, on the Kovanov homology side, we have colored invariants, like colored Jones polynomial. And colored Kovanov homology. Maybe I should write down there. We'll do that. Which we can, well, one way to describe, for instance, color, which, let me first say that the N colored Jones polynomial comes from considering n+1 irreducible representation of SL2, but combinatorially or like diagrammatically, you can also describe it as a limit of the Jones polynomial of cables. So let me remind you again what a cable of a knot is. Like, if I have a frame knot, like my knot K on the left in this picture, and if I have a torus knot or a torus link, like this T and L, here I have a T2, 3, then I can remove a neighborhood of my frame knot, and I can insert my torus knot or link in it to get a new knot or a link. I'm going to denote that by K and L. And it's going to be a link if N and L are not co-prime. And for most of this talk, they are not going to be co-prime. L is going to be M times N, so we'll have an N component link. Okay. So for the Jones polynomial, we can describe, for instance, the n-colored Jones polynomial as the limit of this, limit, we need T, whatever. Sorry, I had Q, and then I realized I wrote everything as P. We K and P. Right? This is Jones polynomial of this cable, and then let's say you are going to change its second grading, quantum grading, by some factor T, and then you're going to insert an infinite twist, or you're going to keep twisting and take the limit as P goes to infinity. Right. Colored Jones polynomial, for instance, appears in volume conjecture. And one of the ways to categorify this is colored Kolmogorov homology. And it can be defined using an infinite twist. So one way to define this n-colored Kolmogorov homology is K, again, as always, is a knot in S3, and we want to insert an infinite twist, which means that we're going to take n copy of our knot K with 0 twist, then n twist, then 2n twist, and so on. Okay. All of these factors need a grading shift. And we also need to have an appropriate connecting map between them. But I guess it goes back to Rosinski. And it's also, maybe I should also say Cooper-Crucial. Sorry. That with an appropriate shift in quantum grading and using appropriate connecting homomorphisms, we can define a categorification of the colored Jones polynomial like this. Any questions? So what is the plan for this talk? The plan for this talk is that we want to use this idea or sort of follow this pattern and define colored not Floer homology. So that will take me to the, I call that the second part, my talk, which is definition.
Sorry, can I have a question?
Yeah.
So that is N0?
Mm-hmm.
What does that mean?
Oh, that just means that you have a frame knot, right? So you just take n parallel copy of your knot without any twist, yeah, in terms of the frame. And now here you just insert one full twist, two full twists, and so on. Yes?
Can you say a few words about the maps of are they coordinate maps?
a great question. They come from this projectors, and I think Paul, which is sitting in front of you, knows better. Or Matt. Yeah. Yeah, that's, yeah. Okay, but in Hager Floer homology, we want to use cobordism maps. Great. Okay. So n-colored not Floer homology. So in order to define n-colored not Floer homology, I want to kind of follow this pattern, which should tell you that I need to look at the Hager-Floer invariance for links. And so if I have a link L in S3, well, Hager-Floer homology, of course, does have invariance for links as well. But we are going to work with not the simplest version, but the full version of link Floer homology, which is, let's say, L has n components. The full version of link Floer homology is going to be a module instead of over F2 adjoint U1 through UN, and we want that through the n. And it will have gradings, and also but before talking about gradings, I also want to say that UI, VI, the action of UI times VI is the same or does not depend on I. So basically what I'm going to do is I'm going to use this letter U sometimes to denote the action. But you can't ignore it. That's just for simplicity. You can ignore it if you don't like it. Okay, so as I said, it will have grading. So it will have a massive grading. So grading. And it will have an Alexander grading, but it's a multi-Alexander grading since it's a link. So we're going to denote the massive grading by M. Well, probably not use it, but Alexander grading by A. And it will have n components, one for each component of the link. Okay. What else I want to talk about link? Okay, not at the moment. Then the n-colored, following this pattern, n-colored link Floer not Floer homology is going to be defined as the direct limit of, let's say, link Floer homology for k n0, link Floer homology for k nn, link Floer homology for k n to n, and so on. This time I'm going to tell you what these maps are and the shift and so on. Okay, so what are these connecting homomorphisms? They are going to be cobordism maps, and here's this part. I'm going to also trace this. Let's say I have an n-component link. I have, and these are distant components of a link. I have an unknot that goes around it. And everything is oriented the same way. Then I can attach a two-handle with -1 framing or do a -1 twist there. That will insert a positive twist into the link. We're going to call this cobordism with just with single two-handle a full twist cobordism. Well, not ending Floer homology, they're functorial, and for these cobordisms, we have cobordism maps. And and depending on which species structure you fix on your cobordism, you get a different map. We are going to denote the cobordism map, phi k, from, let's say, L prime. We are going to denote this cobordism map from link Floer homology of L to link Floer homology of L prime by phi k when the species structure that we fix has first year in class evaluated on the second homology equal to k plus 1. So some integer. For any integer, you will have a species structure. And I'm going to just record that k here inside. Oh, the second homology class, well, that was an unknot, and we are attaching a two-handle to that, so that will give you a second homology class. Yes? Yes, n is the same as the number of components of the link. Why am I doing this like that? Just sort of like, there is another, let's say, the algebra looks nice when you do it this way. There is another sort of construction similar to this that they use, I think, n and maybe n plus 1 cables that all the way you have knots. And they use the hat theory, HFK hat. But the algebra looks nice. And also this is like maths, if I remember correctly, work for coloring and Kovanov homology. K is a knot, yeah. I start with a knot, then I will get a link and then, yeah. Yeah, for the n colored, I get an n component link and take the limit, yeah. Yeah. If you have a link, then you can have different ends for different components. Yeah. Other questions? Okay, great. So now, this phi k's, we know by work of Ian, I guess he's the first one, Ian Zemke, how they shift the massive and Alexander gratings. The massive grating shift by this phi k's is, so grating shift. Phi k. The massive grating shift is negative k squared minus k. The Alexander grating shift is n minus 1/2 minus k, n minus 1/2 minus k, and so on. The same in degree. Okay, now I realize that I have 2k, but this one that I tried to write down smaller, that's an integer, this k is a not. But I will stop doing that after this. So, here. Right, so if I take k equals 0, then this will be 0, and these guys will be n minus 1/2. Right, so I'm going to use connecting homomorphisms that are equal to phi 0. Then that will give me a massive grading at the end. But to get the Alexander grading, I need to shift the Alexander grading on these pieces so that I get something graded. So I'm going to define, well, it's just a fixed notation, but we are going to renormalize Alexander grading and say HFL stabilized, that's the grading that will stabilize anyway, for this K and Mn, one of these pieces in degree S is going to be HFL of K and Mn, and then S needs to be, do I need to shift it up or down? Sorry, this S is S1 through Sn. It's plus M times n minus 1/2 through M times n minus 1/2. Right. So renormalizing Alexander grading this way, I will get something which has both Alexander and Maslow grading. Okay, so the next natural question is it finite dimensional in each degree? Which the answer is yes. Okay. Right, I want to tell you a little bit about the proof. So let's say idea of the proof or sketch of proof, whatever you want to call it. Okay. Well, any questions before that? I guess. Yes, all of the maps are phi 0. Yes. I will tell you. I will tell you. Yes.
And then in the end, the thing you guys supported in like Maslow theory is positive, is like maybe arbitrarily positive or arbitrarily negative, or do you know?
Massive degree stays fixed, right?
Powers get high, so.
Powers are the ones that we get in. Yes. In the examples that we, the ones that we can really compute are just unknot and L-space knots, and the massive gradings will, for all of the massive gradings that you have something for the knot you started with, you will end up getting something at the limit as well. But, it's supported exactly in that, yeah.
Always is.
Yeah. But I think the ones that we calculated are not the interesting examples. Other questions? Yes? Hmm? Okay, that's a great question. There is a Alexander polynomial. We don't know if it categorifies that, and I will tell you why we don't know in a second. Yes? This is, does the finite dimensionality and how you can prove this doesn't have to be knots for in 3 sphere. What do you mean?
Because you fixed them, you've only some of them at, you fixed some spin-C structure, so
Yeah.
when you're in the 3 sphere,
Oh.
it's okay.
Oh, you mean, yeah. Okay. but I'm just looking at them. Okay, anyway, I haven't thought about the I know what your concern is. I agree when we get to the module structure part, but like just formally defining it like this, still, it is a 3 right now. Yeah, that I agree. Yeah.
You can form the Euler characteristic of it, and does it satisfy scheme relation? I mean, it's kind of questions from another point of view.
Well, the problem is that we're going to limit and we're not.
It's not a polynomial, but it's going to be a series, right?
Oh, this.
It's a well-defined theory with 2 gradients, so you can form the.
That's true. No, I agree that we can. I don't know whether it's the it's the same thing as quadratic sum. That's all I'm saying. I agree. Yeah, we can do that. I don't know if it's quadratic sum.
The point is whether it satisfies some kind of scheme relation.
Yeah, I know. Okay, that's fair. That's okay. We should check that. All right, great. Thanks. Yes.
Do you have an action of Sn on this object?
Great questions. Great questions. Yeah, since we're working in S3, yes, is it just like switching things that goes back to the Sn action and link Floer homology? Hopefully. So my student Gary is actually thinking about that. So yeah. Good questions. Okay. Great. So I promised to tell you why we don't know that whether this is really called Alexander polynomial or not. The reason is that this, like, you want to prove something like this, that this is finite dimensional. Well, how do you do that? You try to show that if this twisting is large enough, phi0 becomes an isomorphism and things are stabilized. But the thing is that we show that when this twisting is large enough, things become isomorphic with each other, but we don't know whether that isomorphism is phi0. So we get an upper bound on the rank of whatever we get in the limit, but might not be able to that. Okay, so so we show that for m large enough, or more precisely, there exists a constant k. Oh, sorry, c. I should not call things k. There exists a constant c such that if m is greater than or equal to c minus si, si is the ith entry of the Alexander grading for all I, then HFL, this renormalized, HFL in this renormalized Alexander grading S1 through Sn is isomorphic to HFL, stabilized, of k and m plus 1 and S1 through Sn. And so I said, is this isomorphism phi0? We don't know. Probably. How does the proof work? So let's say up there I just draw a Hegel diagram for trefoil. Well, right hand or left hand, that I really didn't check. So, but as you see, it's a genus 2 Hegel diagram. Why did I draw the genus 2 Hegel diagram? Because I like it. So if you have a Hegel diagram like this, how do you get the knot? If you connect Z to W away from the alphas and also Z to W away from the betas with an arc, you can push the first arc into the alpha handle body, the second arc into beta handle body, and they will give you a knot in your 3-manifold, right? So I want these two arcs to be disjoint, and you can always do like, or only intersect at the endpoints. So you can always do that by increasing the genus and stabilizing. This is, for instance, the genus 2 case that the arc that connects Z to W, which is here, is disjoint away from the alpha. This one is disjoint from the other one that goes everywhere. Right. Okay, now what I'm going to do is to get a Hegel diagram for one of these links, I'm going to replace W with NWs, W1 through Wn, and replace Z with NZ, Z1 through Zn, and then insert some diagram like this. If you put this diagram on S2, that's just a diagram for T, let's say 3, 2. It's just a diagram for the torus link, but you want to put it on the Hegel diagram of the knot. And how do you do that? You sort of do it in a way that here, like these guys are in the same region as W. These guys are in the same region as Z. This part is kind of parallel to the arc that connects it to W away from the beta, so you don't see any beta intersection here. And this part is kind of parallel to the arc that connects Z to W away from the alpha. And here, for these alpha circles, we don't have any twisting, but for the beta circles, we'll have the right amount of twisting around the Z base points to get the right, so like if you want to get the diagram for K and Mn, do the appropriate amount of twisting. But to be honest, like since we're taking the limit, it really doesn't matter which framing on K you start from. So I'm going to just, at the moment, just assume that I twisted M times in order to get the diagram for K and Mn, and that K and M is not the one you get from the zero framing necessarily. Okay, now, if I move this Z base points, so this new alpha and beta that I added, these new sets of alphas and betas that I added, they will intersect each other here and in sort of blocks each time that they wind around the Z base point. If I move the base points from this region to here, then I will get a diagram for the knot with one less twist. This trick is what Matt Hedden also uses in his thesis for studying cables of knots. And if you were at the What's Your 3 conference last year in Boston, he talked about this. So in this way, we can see the diagrams for like 2 of these ones, or if the number of twists is enough, any 2 of these links in sort of the same picture, but we're just moving the Z base points. And what happens is that what we show is that if the number of these twists gets, okay, let me first say one more thing. So if I look at the 2 diagram with M and M plus 1 twists like this, one with base points here and another one with base points here, or Z base points there, then they will have the same intersection points, sort of the same. This contribute to differential, they contribute differently. And depending on the spin-state structure, you need to multiply them by, depending on the Alexander grading, you need to multiply them by different monomials to get the generator in that Alexander grading. But what we can show is that if the number of twists is large enough, the 2 chain complexes are really isomorphic to each other using diagrams like this. And this C comes from how big is the difference of Alexander gradings for intersection points when you just have one single twist in your diagram. Okay. Any questions? Yes?
Does it make sense to do this at the border level? Can you do it in the border level for
That's it.
other
Yeah.
subjects?
That's a great question. Yeah, so we did look into Ian's work because we're doing minus theory, right? So one tool to do minus theory in the border world is Ian's work. We did look at the algebra. It seemed to, at least when we were looking at it, it seemed to kind of hard to single out one spin C structure and versus adding all of the spin C structure for the cobordism map. Like to read that off from the algebra. That, yeah. Other questions? Yeah, but anyway, this isomorphism that we're constructing is kind of using diagrams like this, which that's why we don't know whether they're really this cobordism maps or they're just the groups being stabilized, but the cobordism maps are different, or the isomorphisms are different. Okay. I'm going to talk about the modular structure on this so that I can describe the examples that you asked me. Part 3, yes. Okay, modular structure. So in order to describe that, I need to tell you a little bit about properties of this cobordism maps. So proposition 1 is that if you look at this cobordism maps, phi k, that go from, this length doesn't really have to be a cable, so I'm just going to write it as L, h of L to L prime. And K, remember that records the space C structure. Then these cobordism maps are actually, there are lots of relations between them. The first set of relation is that if K is greater than or equal to n minus 1, then everything can be described by phi n minus 1. So phi k is equal to some monomial, which I need this to u1 through un to the k minus n minus 1 times that bold u, which is just a uivi, k minus n minus 1 times k minus n over 2. Is that correct? Yes. Times phi n minus 1. And if k, so the takeout is that you just have some monomial, and you can compute this exponents by just looking at how these two shift the Alexander grading. But some monomial times phi n minus 1 will give you phi k for any k greater than or equal to n. And if k is less than or equal to 0, then everything is given by some monomial times phi 0. So phi k is something times phi 0. Again, you can just ignore this part, some monomial times phi 0. And you might say, why that's minus k, but this u is uivj, so this can be really described with something with positive exponents. Okay, and if k is between 0 and n minus 1, then we can look at all of the subsets of 1 through n with k elements and multiply phi k by ui. This ui is product of ui's in this subset I in I. And it's equal to V complement of I times Vk plus 1 or minus 1, say k minus 1 Vk. So everything is, there's a nice kind of polynomial relation between all of these Fordism maps. And where are these relations coming from? That's also a functoriality result, which is, you can kind of see it in this picture. So what is the first row? The first row is really, I'm not doing anything, but I'm just telling you a different way to look at your cobordism. Instead of just looking at your cobordism as attaching a single two-handle, you can think about it as generating or birth of disks, n disks. So that will result in an n-component unlink next to your link. Then you can attach bands between the unlink and your link. So you'll get back your link. These are just canceling each other. And you can do your two-handle here to get to the twist. But then if you do that, you can switch the order of the bands and the two-handle. So you can first do the two-handle and then attach the band. So using, okay, I'm ignoring that things are decorated in their basement. That's fine. They all work out thanks to Ian. So, but you can say that using the functoriality of link Floer homology, you can say that if I want to prove relations like this between my maps, I can just prove them for going from unlink to the TNN when inserting full twist, and I don't need to worry about. So it's like if I prove it locally for unlink to TNN, then I'm good to go. And well, these type of things, checking them for unlink to TNN, it's not really hard because they're L-space links. Everything is determined by gradings. So if we know how the maps shift the gradings, then we know relations between them and so on. So that's how this proposition has been proved. We check them for unlink to TNN, then we use functoriality to show that relations between them is, they're going to be hold for any full twist cobordism. Okay, so, but why is this helpful to, for us to describe a module structure? Let me write down the second proposition here, because the second proposition is that if I go from my link L to a link L prime with cobordism phi k, and L prime to L double prime, full twist cobordism phi L, so we are inserting two full twists at the end, or go from L to L prime, sorry, with phi I, and then L prime to L double prime with phi j. And I plus j is equal k plus L, and I is less than or equal to k, less than or equal to L, less than or equal to j, then I will have a quadratic relation between these things, which is phi I, phi j is equal to u KL minus IJ, phi K, phi L, maybe I should have said JI, L, phi K. This one really needs to work on S3. Anyway. Okay. Maybe I should have. Yeah.
I and J also important, or is it just that you want the two steps?
I wanted this to be positive.
J is really the longest one?
I mean, then it will be negative, right? This sum is equal to each other.
But I mean, if you sort of change I
Oh.
and j,
Change I and j.
then KL minus IJ is still going to be positive.
I don't think that matters, to be honest. I think that's.
So the more, I mean, it's just a matter of which
I
two
think that
are
doesn't
better.
matter. Yeah. It's just not. Yes.
You end up choosing an element in the Lindgren market segment by the image of the current standard that you have come out. How canonical that is? Isn't anything that's like
Can
do you know how canonical that element in the Lindgren market is?
Like link Floer homology of TNN, everything is given by the H function and the grading, and like, what do you mean? I mean, if you write down the Alexander polynomial, and then you can write down the whole homology, and then the image of every map is given by whatever grading you should land on. So if you compute the shift, what am I saying? What I'm saying is that if you compute the grading shift of your map, then you know where you will end up. So in your link Floer homology. Yeah, these are like L space knots. Just okay. Other questions? Right. So yeah. Okay. The order of K and L and I and J really doesn't matter now that K and L can be solved, I and J can be solved. Great question. So then we'll get an action of, so let me define this algebra before I erase these relations. We can define this algebra AN to be the F2 U1 through UN, V1 through Vn module, or say algebra, generated by A0 through AN minus 1, and I'll go to AN minus 1. A0 to AN minus 1, and relations which is linear relations UI a k minus 1 is V I bar a k. Well, compare this with this relation here. It's exactly that. So I is a subset with k elements, and I bar is the complement of that. And we have quadratic relations, which is AIAJ is equal to U K L minus IJ A K A L. And it's a commutative algebra, by the way. Okay, so this is basically just an algebra describing those relations between the cobordisms. And this will act on the direct sum of, in a very trivial way, if we take the direct sum over n of this h of L, sorry, m, k, n, m, n, this is going to act on that. Right? So how AI acts as phi from on this summand k and mn to and yeah, just defined in a way that this will act like that. Okay, so great, but let's have an example. I'm going to call this cab n of k. For the unknot, this is just going to be an. And what I mean is just going to be rank 1 modulo over an. This is really uses heavily the result of Brodzik, Leo, and Zemke that tell us how to compute these things. And I'm worried that I wrote, okay, maybe. So using their result, one can describe all of these link Floer homology of all of these torus links by computing their Alexander polynomial, and then it's a bunch of algebra to show that this is actually that. It's like everything. Okay. Great. So, but that's not what we were looking for. We were looking for a quotient of this guy, not itself. So, what's this part? But that's easy now at this point. So, h n of n of k is a quotient of this by this phi 0 action, right? And here, we need to do, in order to get the module structure, we need to localize this, or do a graded localization of A0, which this guy is just a span of, let's say, y over A0 to the m, where y is homogeneous of degree m. So it's graded. Okay. Great. But what is this? Well, when you invert A0, then this will simplify a lot. It's going to be the quotient of, I'm going to first describe this version, but then we'll write down the simplest one after that. Quotient of this with just an extra element added, mod out with ui is identified with v1 dot 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 dot, vi is removed dot dot dot, vn times this a. So that's how this a is related to the action of v's and ui's. And this is, well, okay, it's just isomorphic to f2 of v1 through vn and a. And what is that a? That a is just, I mean, if you go back to that description, this a under this isomorphism is just a1 over a0. Which is like kind of comparing phi1 and phi0 actions. So our colored invariant will have a structure or have a modular structure over this, this guy, which is actually isomorphic to the polynomial algebra with n+1 variables. And I'm just going to finish by telling you two examples and a remark. First example is the unknot example, which is hn of the unknot is just that. And if k is an L space knot, then Hn of k is also not that interesting. It's just going to be H of k tensored. So H of k is a module over F2 adjoint U and V. So I need to give you a homomorphism alpha. Just say, I'm going to write it like that. What is this homomorphism alpha? It's going to be alpha of U is equal A, and alpha of V is equal to V1. Great. So these are so far the only things that we could compute because, well, both of them you can compute phi zeros by the gratings. Great. Now, the remark that I wanted to make is that this story that I just told you really didn't have to work with cables, right? You could have started with an oriented link and a disk that intersects each component of the link at exactly one point, and a knot that bounds the disk that intersects each component of the link at exactly one point. They're oriented the same way, and keep inserting twists and take the limit. And at the end, the things will stabilize. It will have a grading, a massive and Alexander grading, and can define something which depends on the link, the oriented link, and the disk. And it's going to be a module over, well, again, we're working in S3, so it's going to be a module over this ring. There is another invariant for these things, which is a module over that ring, which is if I sort of take my unknot and just squish it and collapse that into this graph with a thick edge in the middle, it doesn't have to be thick, but whatever, then the invariant that would define for graphs, which is kind of like, I guess, minus future Floer homology and VM in me and Eftekhari, this is also a module over a polynomial ring with n+1 variables. And I want to finish with a question, is there any connection between those two? One might think, maybe, yeah, right? We are doing twisting a lot, why not? But I don't know. But if there's a question, if really there's like, if really these two are the same, or they are isomorphic, or there's a, like, if you can compute this out of that, so then maybe something like this is really true for any knot K, and it's not really more than not Floer homology, but I don't know. And I don't know how to prove something like this or whether they're related. But yeah, I'm going to stop here. Questions? Yes.
I don't know a ton about this, so you might have said something during the talk, but can you say anything about the relationship between this invariant and like thinking about a large surgery formula on like an end cable, since this is kind of like a large surgery?
Is it like a large surgery? I don't,
on the
yeah.
Floridian.
I don't, I haven't thought about it, to be honest, maybe, which is not a good answer, but yeah. Let me think about it.
Something very similar to this.
Uh-huh.
Circular. So what if you do, if you attach a two handle to your knot to obtain a four manifold, and you get the skin lasagna of the Floer version, kind of seems that there is a map from your construction from this skin lasagna.
Yeah.
Is that right?
That's a good, I don't, yeah.
When the starting point, you have all these hand versions and all these caps with basically
Yeah, to be honest, we started with which one we can compute. Can we compute twisting when everything is oriented the same way, or can we compute with like oriented like the lasagna ones? And we did this one first.
The Floer version, I think if you kind of model out for the actual homology,
That's
you
the
can get
same.
rid of that ambiguity with, I mean, that some of them go this way and the other way. That I think can be.
Okay, yeah, I
So
should think
I
that.
mean, at least the zero term exactly look like your whatever function at zero.
Okay, let's talk more about that. Thanks.
This is
Yes.
perhaps a naive question, but this question mark in purple,
Mm-hmm.
does this have a connection? I think you mentioned earlier that you're not yet sure if this categorifies the colored Alexander polynomials in the appropriate sense. Are those two things related, or is that a separate question?
They're both interesting questions that I don't know the answer to. And I also, the thing is that if you ask me, does this, the categorification of this, is that Alexander polynomial? I don't know. Yeah. It's a great question, though. Yeah. Yes.
So I guess I have two related questions. First off, is there supposed to be symmetry of this whole story that exchanges like phi 0 with phi n minus 1 and exchanges u with phi's? And then my second question would be, what happens if you repeat your story with phi n minus 1 instead of phi 0?
Yeah, you can definitely do that. You can use any of the fees to
Like,
do
I
this
was a little-
story. Then,
Yeah.
then you need
I was a little
shifts
confused
and
by the relations. They didn't seem to treat even phi symmetrically.
yeah. Well, it's oriented, right? Yeah, like things are oriented, right? But there is a little bit of, I know what you're saying. I think it should not say, I feel like that's like switching U's and V's, and if that's true, then yes, you just like, right now I'm twisting near Z's, and the whole argument if I twist near W's, then probably will be what you're looking for with using phi n minus 1 instead of phi 0. But I'm not, yeah, I need to sit down and actually look at it, study it. But yeah, there is, okay, let's say there is really nothing special about phi 0. That's probably the better answer I want to give you. It's just, it doesn't shift massive grading, so the things are cleaner. Yes?
What's the relation between this thing and the Quantum version?
Great. It's a great question. I can, for the unknowed, that's the only thing that we can really say anything about, which is not really that interesting. I can show you the algebra afterwards, but like in general, I don't know.
Yeah. Asking what is the underlying, it's a modular structure. The quantum version is also modular over some ring.
Yeah.
What's the counterpart of A?
Yeah, this is a module. Okay. I need to check my notes, but this is a module over whatever you get for the unknowed, and then you can compare the ones for the unknowed. So yeah, I can show you how the modules are related.
A
Yeah.
lot of homology computation isn't in the literature right now, so I think your question is a better one than you realize. We don't really know how to compute all these things yet in a lot of sense, but
Yeah.
maybe people are working on it.
Even for the unknown.
Yeah, it's hard to compare with quantum stuff, but it's much harder to compute.
But I think it should be compared with the Wi-Fi things, right?
Yeah,
The color.
Wi-Fi,
Right?
we can talk, but it's
Yeah.
there's no place that you can point to in the literature where the answer is right now. Yet, but possibly soon.
Yeah.
Promise or threat?
Uh,
Is that a promise or a threat? That it'll be in the literature soon.